Good morning. It's a pleasure to be here. My name is Ed Nightingale, and I've been working for the last 3.5 years on a project that started as research incubation at Microsoft Research called Azure Sphere. And it was a third person to join this project with Galen Hunt, and stepped back and looked at where we felt kind of the next big wave was going to be, and looking at IoT and looking at security, and decided to make a bet on that. And now, 3.5 years later, we're a publicly announced product, growing team, and it's been a pleasure today to kind of tell you about the motivation behind Azure Sphere. I think what you'll find is interesting tidbits about the silicon architecture as well as the operating system architecture, some of the principles we have behind this product, as well as looking forward a bit. And we think about mobility, we think about IoT and the opportunities that I see in the research space. So, what is Azure Sphere focused on? Azure Sphere is focused on microcontrollers, and these really are low-cost single-chip computers. These single-chip computers just cost a couple of dollars. There are over 9 billion MCU devices that are sold around the world every year. And these devices are all around you. You know, I think of Mark Weiser's original paper around pervasive computing. Microcontrollers have really fulfilled that vision, I believe, fulfilled that prophecy. They are the fabric of computing that you never notice. They're in your hotel room, in your office, in your home. Anything that has a low-res display or a set of buttons is running a microcontroller. Now, only 3% or 1% of these microcontrollers around the world are connected to anything. And you might ask, why is that the case? Well, for a long time, it was just simply too expensive. But then something significant happened about 3 years ago, is that you started to see the first single-chip microcontrollers with a built-in radio. And so what this meant is that for a few dollars, you could take any device and you could connect it to the internet. Now, when I think about this case, I think about the fact that for the last 30 years, microcontrollers are really what I would call a fire and forget scenario. If they're running an alarm clock, if they're running an ATM, even if they're running any embedded computing scenario, you write the firmware once, you get it mostly right, you launch it off into a device, and you never look at it again. It gets used every day, people push buttons in the device, and you don't have to worry about it. So what's the idea behind connectivity? I don't think this audience is going to have to be convinced about why connectivity is important. We're going to run through just a couple of examples anyways. So when I think about your refrigerator, and that we all have, why is a connected refrigerator useful? I get asked this question a lot. A simple example is that how do you know your compressor needs to be replaced? Option one is that you get up in the morning, you come downstairs with your family, you have melted ice cream all over the floor. You've got, at my house, I'd have a serious problem with that. My kids would be very unhappy. Option two is that you get a phone call, and the phone call says, hey, your compressor is starting to fail. We've got some ultrasound sensors. We noticed it's starting to vibrate. Is it okay if we stop by today and replace it? No melted ice cream. I don't think anyone would argue that this second experience is a better one in terms of connectivity, in terms of the experience you have with the devices around you. But it's going to require connectivity. Even more concretely, this is a product now that's in what we call public preview, so people are evaluating it. But it's been so compelling that Starbucks recently announced in January that they're using Azure Sphere to connect all of their coffee makers in all of their stores around the world, 58,000 stores on the internet. Now, why would you want to do that? Well, maintenance is one reason. We just talked about that. But there's another one that's really interesting. All the coffee makers in Starbucks have recipes. You say, well, what do you mean by recipe? Well, just as a simple example, you have a motor for a grinder to grind beans into coffee. And that grinder, because it's software, has parameters that you can put in. And the beans themselves change throughout the year. The density changes, depending on the weather they change, they look different. And so Starbucks, to make sure you have a good cup of coffee, actually changes the parameters in your Starbucks grinder. You say, well, how did they do that? Well, they would send people by hand with 8,000 USB sticks and go to every single coffee maker at every Starbucks around the world twice a year and plug them in manually to update the parameters to get a better grind. Now, that's incredibly costly. And you say, well, why did they do that? Well, they had coffee makers with MCUs and with a little Ethernet port, and they said to their vendors, is this secured? And of course, the vendor said, of course it is. They said, well, how? And there was a lot of uncertainty. So they really didn't trust the platform, because if a coffee maker is attacked in a Starbucks, that's dollars out the door, right? That means it's something that's not going to function anymore. They're losing money. So when you think about this, think about the opportunity around IoT, the opportunity around taking these 9 billion devices and having them all be connected, the ability to deliver new experiences to you day to day, and if there's some value in those experiences, you might even be willing to pay for them. But there's also a tremendous amount of risk. So, ask you, when you look at the news, what happens when you connect a device to the internet? Chaos and disaster happen. I don't think there's a week that goes by that someone from our marketing team doesn't forward me an email about something going wrong with IoT. You've got refrigerators sending spam, which is one of my favorites. You've got baby monitors that are spying on you. You've got hackers infecting routers all over the world. And the most significant of these attacks, the kind of the watershed moment for us as we were working on this at Microsoft Research, was the Mirai botnet. So the Mirai botnet happened in the fall of 2016, and it effectively brought down the East Coast routing of the internet and brought it to its knees. And there are 3 key points about the Mirai botnet. This was launched against an internet-connected camera, a cheap IoT device. What's important to note here? Well, it's only 100,000 devices. So this is just 100,000 cameras. If you look at 9 billion devices, any what we call vertical, any area of industry, consider household appliances that many of you have in your apartments or your homes. There are 300 million household appliances sold every year. So if 100,000 cameras can take down part of the internet, think about 150 million refrigerators that all just decided denial of service attack. It would be catastrophic. The other thing that was really depressing to me is exploited a well-known weakness. These cameras had a default password. It was ROOT. You couldn't update the password or change it. You weren't allowed to. It was fixed. And even worse was that when the manufacturer found out that there was this fundamental problem with a fixed simple password, they had no ability to update the firmware remotely. They basically said, go to this website, download this thing to this USB stick, and connect up a connector, which of course no one did, because that's too complicated. My father wouldn't be able to do that. He would just unplug it and throw it in the trash if I convinced him to. My other favorite is this casino. The casino had a very expensive aquarium, and they wanted to monitor the temperature. They wanted to connect it, so they put a connected thermometer into the aquarium. And the thermometer was on the same network as the high roller database, and someone managed to produce a sequence of attacks where they hacked into the thermometer, and then they hacked into the high roller database and stole it. Now, you might say, wait a minute, why is someone so foolish to construct a network where there are internet-connected thermometers on the same network as their backend database? I would say, why does a casino have to be so smart that they have InfoSec people to construct a network like this? People just want to connect things to the internet. And I feel like this is really, as a group, both in research and industry, we're behind. The people are launching ahead because of the value they see in connecting everything they can to the internet really cheaply, and we're seeing the after effects. So I'm going to beat this dead horse one more time. When you think about our refrigerator example, you come downstairs and we talked about a nice experience where somebody calls you and says your compressor's failing. What's the negative experience? The negative experience is you wake up, you come downstairs for breakfast, you look at your phone, and there's a text message that says, this is hackers, we pawned your fridge, give us $5 in Bitcoin or we melt the ice cream. That's a bit facetious, but I know is not out of the realm of possibilities of what we're seeing right now. More seriously, we did talk to a manufacturer of appliances about this, and they laughed and said security is not a problem. Then they actually did an audit and a pen test and discovered they had a stove that was not yet released, that someone discovered you could chain a series of attacks together. You could light the gas on the stove and ignite it an arbitrary amount of time later because it was a variable in software. And so this is the thing that worries me the most, is wake up one morning, 100,000 stoves have exploded. The insight here is that microcontrollers have gone to being fixed purpose, which is how the industry that builds microcontrollers thinks about them. They do one thing well. They push a button, they set an alarm, they light a stove. Once you connect something to the internet, every microcontroller has the capability to be a general purpose computer. And a general purpose computer in the hands of an attacker can mean you're going to have chaos on your hands, or the potential for chaos. So, security is foundational, right? It has to be built in from the beginning of the product. And this is where Azure Sphere comes in. So what is Microsoft? What did we start with in Microsoft Research when we looked at this space? The first thing was we looked at properties, and then I'll talk a little about product. We published a little white paper called The 7 Properties of Highly Secure Devices. It's at ak.ms, 7 properties. I'd love your feedback. If you haven't read it, please take a look. Let us know what you think. And these 7 properties was our point of view and putting a stake in the ground that said any device that's connected to the internet has to have a minimum set of properties to have any chance at being secured. We're not saying that if you have all these 7 properties, you can't be hacked. Of course, we all write bugs in software, it's going to happen. But if you're going to connect to something on the internet, you must have this minimum set of properties. Now, why are these properties important? Most people in industry don't have the expertise or know-how to do a deep evaluation of security. And they might ask their supply chain, hey, I've got this connected thing, is it secured? And no one is going to be told no. So part of us writing this, besides putting a stake in the ground, is to give people a simple set of questions they can ask. To ask, is the device we're developing secured or not? Does it have the base foundation to provide an experience that's secured, that provides some defenses against attackers? So I'm going to cover just a few of these. But again, please take a look. I'm happy to hear feedback on this. I love the conversation. What are we missing? Where can we do better here? So some of the properties depend only on hardware support. So the fundamental key here is a hardware-based root of trust. So unforgeable cryptographic keys, generated and protected by hardware. I'm going to get into that in a second. This hardware protects the device identity, so it can't be impersonated. It's hardware for secure boot, which means that with secured boot in a set of keys, you're going to eliminate malware being affected on a device, being put in a device, or unsigned software, and also hardware to attest to system integrity. And I'll get to what that means in a few slides. So some of the properties that depend on hardware and software. So we call this dynamic compartments. These are internal barriers to reach the limit of its failure. What do I mean by that? With operating system parlance, this is about having an MMU and process-based isolation. I'll get back to that in a second. This is the most provocative property that we have in this list of 7, and I'll talk a little bit more about why it's provocative and why we get a lot of feedback on this one. And then some of these properties depend upon hardware, software, and the cloud. So you need the cloud to provide updates. You need software to apply those updates, and you need hardware to prevent rollback attacks. So what is a rollback attack? Secured boot ensures that you don't have malware, you don't have unsigned software. But a rollback attack is when an attacker takes the old version of your software that's signed and legitimate but has a known vulnerability and tricks your device to rolling back to it so it can be attacked. So if you think about connected devices on a large scale, anyone who can trick a device into a large-scale rollback attack effectively undoes a patch to make the device more secured. The only way to guarantee you don't have a rollback attack is if you can do something, what we call e-fuses. E-fuses are write-once memory in a device. You can blow a fuse and guarantee that a software below a certain version is never allowed to run. So that's properties. Let's talk about what this product is. Azure Sphere is basically an end-to-end solution for securing these types of MCU-powered devices. So there's 3 pieces, 3 pillars to this Azure Sphere system. The first one are Azure Sphere we call certified MCUs. These are built by silicon partners. So we have one in the market built by MediaTek. There'll be more coming. That has built-in Microsoft security technology with a dependable hardware root trust. Now, why is that Microsoft security technology? I'll get to that in a few slides. I'll actually take the opportunity with this audience to do a deep dive and talk about some of the differences in this piece of security technology that we're giving away for free that doesn't exist in a lot of existing hardware roots of trust. The other piece is the Azure Sphere operating system. Basically, we're guaranteeing we're going to provide updates to this operating system for 13 years. It's a Linux kernel at its core, and it's been trimmed down to fit on these low-end devices. And I'll talk about some of the changes we've made to make this a more secured operating system than the default one you typically get with Linux. And the last is the Azure Sphere Security Service. So this is security service that's all about brokering trust. So it leverages something called remote attestation, which I'll talk about a little bit later, to effectively create a token that allows Microsoft to vouch for the health of the device when it connects to the internet and prevent a device that is untrusted from making a TLS or a mutually authenticated connection. So this is the 3 pillars of Azure Sphere: silicon, OS, and services. And what's interesting is that when you look at security in a lot of the MCU deployed systems, you might have someone who's an expert in silicon, and they say, look, we've got a hardware to trust, but then you say, how do I update it? And they say, well, you can't, or you have to go somewhere else to update it. You might have someone who's looking at a service to do updates, but then they can't necessarily trust the endpoint because they don't have mutual authentication as an example. They don't require a hardware to trust. And in terms of the operating system, I'll get into this in a little bit, but we sign everything Microsoft signs every piece of software. So third-party signing is only secured as the infrastructure that protects it. So by requiring one group to sign everything, we are betting on our basically key signing infrastructure. So I'm going to cover each of these pillars in turn and talk a little bit about them. And this is going to be a bit more of a deep dive into silicon, because I think this is where some of the most interesting pieces of the architecture lie. This is a cartoon, what we call a cartoon, a silicon cartoon of an Azure Sphere chip. And so you've got Pluton. Pluton is the, gosh, this is not going to happen. Oh, that's blinking it. Well, Pluton is the Microsoft-based security IP. It's our hardware to trust. And one thing to note about Pluton is that, unlike a TPM, is that it's on die. And I'll talk a little bit about why an on die hardware to trust is significantly more important than an off die hardware to trust when you think about physical tampering. I'll get to that in a little bit. We also have flash. There's minimum 4 megs. It's actually, we have 16 megabytes of flash, 4 megabytes of SRAM. That's also on die. That provides a significant amount of security compared to off die, or what's called in-package RAM. We have a Cortex-A, which we're calling a crossover MCU. This is not something you typically see in an MCU. An MCU typically has 200 kilobytes of RAM, 300 kilobytes of flash, sometimes 70 kilobytes of RAM. So we have a Cortex-A. Why do we have a Cortex-A in this space? Cortex-A's have MMUs. MMUs mean process-based isolation, and it gives you a set of ease in terms of programming, as well as security that you simply don't have with an M-core or a typical MCU with what's called an MPU, which is a memory protection unit that doesn't provide address translation. And we also have some Cortex-Ms. The reason we have Cortex-Ms is for hard real-time. A lot of the cases with MCUs and with IoT is that you need this hard real-time to do something, to interact with a sensor, to interact with some sort of external peripheral that you need deterministic timing on. So I'm going to dive into each of these in turn. So this is the hardware to trust for Azure Sphere. What does Pluton gives you? It gives you authenticity. So this is a secure boot through ECDSA, which guarantees that only signed software runs the device. And everything must be signed. It's not just the bootloader, it's not just the OS. Every single application that runs in Azure Sphere has to be signed. There's no way to run unsigned software. It protects against downgrade attacks. I talked about that attack a little bit ago. We can actually have the ability to blow a fuse and guarantee that an old version of the software that's known insecure, let's talk like something like crack, can never be run again. It guarantees authenticity of your device itself. So when we talk about an MCU like this, as it comes out of the manufacturing facility, it generates keys. And the public key is sent to Microsoft so that we effectively have registered the device as it rolls off the assembly line. Then as it travels through a supply chain and appears again, we can actually tell, because we've seen this private key before, that it is a Azure Sphere chip, and then we can go through a mutual authentication exercise to prove that it's an Azure Sphere chip. Reduces supply chain risk. So you can look on the internet. There's a story about 20 models of Android phone that were taken over in a warehouse in a supply chain attack, where they basically rooted them and then put unsigned software on them, so that when they were opened as new phones, the cameras and microphones were already recording. So it's important that you don't have a way to root these devices to run unsigned software. We can talk later, or talk at coffee, about, well, how do you do software development to a device that doesn't allow unsigned software? What does that mean? We can talk about that in a moment. We have a whole mechanism around that. It also accelerates typical cryptographic tests. It's ECC as well as AES. And it protects against low entropy attacks. So Azure Sphere has a true random number generator. It takes entropy from the environment. It measures its own entropy. It has a set of parameters that detects whether the amount of entropy generated is enough, and shuts itself down if it isn't, so it won't generate random numbers. This is incredibly important early in the process when we generate keys. So often in an MCU space, if there is public-private cryptography, the keys are generated with something called an HSM, which is a separate device in a factory that generates private key pairs and then sends them across a wire into the device. That's not secure enough, because there is this opportunity where the private key is exposed, and you never want private keys exposed. So Pluton actually generates its public-private key pairs using this random number generator in silicon. So even the most trusted piece of software in the device that we've written can never read them. It's impossible. The only way to read the private key in an Azure Sphere chip is if you bathe the chip in acid, decap it, and then use an electron microscope to extract the keys. One of my security experts on the team has an electron microscope. He's tried. It's pretty hard. But we're not, one thing to be clear about is that we're not defending against well-funded nation states. You might laugh about that, but we had a serious conversation when we looked at these chips about, are we defending against a well-funded nation state extracting private keys? And we're not, because of the price point. If you want to defend against a well-funded nation state, it's virtually impossible, and it's something that we're not offering a guarantee against. A lot of other guarantees we provide, but we can't provide that one. So a low entropy attack is when someone effectively reduces the amount of entropy in a chip, causes your random number generator to have less randomness, and then weakens things like cryptography. So, just to summarize some of these features in silicon that Pluton provides, that's often provided not in silicon but in software, a hardware to trust that accelerates common cryptographic tasks. It generates its own public-private key pairs in silicon to guard those private keys from anyone ever being able to see them. Implements secure boot versus ECDSA. It's a dedicated separate core and memory. So Pluton actually has its own private tightly coupled memory that resists attacks like Spectre and Meltdown that depend upon having code executing concurrently and different cores on the same chip. A true random number generator that defends against low entropy attacks, and measured boot and remote attestation. It uses a digest accumulator register and a nonce register. I'll get to that in a moment, but why that's important. But effectively, by keeping measured boot in silicon on die, you can guarantee that even if your most trusted portion of your code has been exploited, that this attestation value can never be forged. One of the issues with a TPM on your typical PC is it's off die, right? And that means when it does a measurement value with attestation, your CPU must send that measurement value. And that means it's traveling across a bus and some wires, and that means if someone's focused enough, they can effectively perturb those wires and send any attestation value they want. By having an on-die hardware to trust, you eliminate that threat vector. When you think about billions of devices deployed all over the world, and we'll get to this at the end of the talk, when I think about the explosion of cheap cameras and facial recognition, and having some sort of privacy guarantee or security guarantee in that space, we care about physical tampering. Now there's limits to how much physical tampering we can resist, as I mentioned earlier, but we do have a set of physical tampering defenses that are somewhat unique in the MCU space. And if I step back for a moment, we're going to keep going through this low level because I wanted to expose you guys to all these different interesting features. Nothing that I've talked about, you would step back and go, oh my gosh, why hasn't this appeared at ISCA? What we're talking about is taking the state of the art that is often viewed as a value add, is often viewed as something you charge more money for because you might have to pay more for security, and forcing it into the low end, forcing it into these very inexpensive devices to make it easier for everyone to take advantage of these types of security technologies. And this comes from a few decades of experience at Microsoft defending certain platforms from physical attack and from hackers. So, Cortex-A. The reason I said we have a Cortex-A on something called an MCU is we think about security, think about portability, and then we think about extensibility. So security, the Cortex-A provides process level isolation via its MMU. This is something that everybody here who thinks about operating systems can understand. When you have an MCU without an MMU, you're basically programming the address space through physical addressing, through something that looks like segmentation every time you write an application. That means you have to get it right every time you write an application. Having an MMU in an operating system that has done this right once means that you have a much higher chance of success. That's why we all like operating systems like Linux and Windows. And this also means that there's this, besides this lack of brittleness, you get a bit more, it's easier to get the security right. So specialist operating systems, this is based on the Linux kernel. Basically what we've done is because this has to run in such a small amount of memory and flash, and because of all these different attack vectors, we've stripped a lot of things out of the operating system. So the Azure Sphere operating system doesn't have a shell. It just doesn't exist. It doesn't have user accounts. It doesn't have any concept of users at all. So it doesn't have passwords. There's no password file. They don't exist. So we've taken is a lot of the attack vectors that you see typically being isolated and attacked on existing IoT devices and just eliminated them, because then we don't have to guard them or protect them. Authentication, so it uses client and server authentication. Again, you often see server authentication in these devices. It's just mutual auth. I'll get into how we do mutual auth and use mutual auth to prove that a device is not only legitimate but healthy a little bit later in the talk. And we also have a custom access control system that leverages Pluton. We use a Linux security module to broadly protect all sorts of different properties of the system, but it's grounded by silicon so that we actually are able to protect flash, RAM, and peripherals. This is just about This is a bit of marketing. It's just about, hey, you got an MMU, you got Linux, it's way easier to port stuff than having to do a custom RTOS and a custom MCU every time you want to do something new. As well, when you're based on a Linux-based operating system, you get to leverage POSIX and open source. It's a big win. I think we all agree with that. And the other thing is that when you typically look at MCU, I mentioned fire and forget. MCU's price is so sensitive in a typical MCU that you buy an MCU with just enough memory to do exactly the thing you need to do and nothing else ever, because you never update it again. That doesn't work in a place where you're doing over-the-air updates, where you have to do security updates. What happens when your security update overflows the amount of TCM you have, or overflows the segment that you've set up to capture part of your RTOS? Well, it doesn't work. So having a bit more RAM, having Cortex-A, having a modern operating system is super important in this space. So that's a little bit about the Cortex-A. Let's talk about what we call silicon countermeasures. Silicon countermeasures are extended beyond Pluton. So this says the word firewall in them. I don't want you to think about a network firewall. Internally, we use a different term. It's called a core mapper. What is a core mapper? Well, the core mappers are granting access to resources in silicon to different cores in the system. So you can grant RAM, access to the network, flash, only through explicit permissioning. And it applies to every resource in the system, especially to peripherals. And I'll get to why that's important in a second. So what this means is that you have no way out because the silicon is protecting against it. So if a Cortex-M, for example, is running something sensitive over an internal bus, and you have another Cortex-M that's accessing a different sensitive peripheral, if one Cortex-M is compromised, it's completely owned by an attacker, and then that attacker tries to bounce through to the other Cortex-M and tap into your peripheral, it's just simply not possible. There's a full crossbar underneath the covers, so you have full access to peripheral, but all of the peripheral accessees get bounced through effectively a set of registers in a core map that guarantees you have been granted permission to another peripheral. So this is a way for us to box in and provide isolation across these different cores. Something, again, you don't see in MCUs, you don't even see on a typical x86 operating system. So they're also sticky. So what do I mean by stickiness in this case? Well, we don't trust ourselves. I mentioned earlier, we use the word secured when we talk about Azure Sphere. It's with a D. It's the past tense. We do that on purpose because you're only as secure as you think you are today. You don't know about the bugs that you aren't aware of or exploits that you haven't seen yet. So all of these core mapping functionality is sticky. What that means is that there's a write once register. So when you boot, you assign a peripheral. Let's say I assign the I2C peripheral to a certain core. Once I flip the sticky bit, that peripheral cannot be remapped until I reset the entire chip. So that means even if you compromise the software that manages these core mappings, an attacker can't remap a peripheral to the core they're on to try to gain access to it. So this stickiness is super important when you think about ensuring that the configuration you have in terms of sensitive peripherals, accessing sensitive objects like a camera or a heart rate monitor, aren't attacked and aren't unwound. The other thing I'm going to talk about that's not in this slide that some of you might appreciate is NOP sled detection and NOP sled protection. So in a typical MCU or operating system, when you access something that's unmapped in the physical address space, we're not about the virtual address space, but the physical address space, you get zeros back, which means an ARM CPU will happily accept that zero as a NOP and just keep executing. So a typical attack is that, for example, if you compromise Linux, that you just start sledding through the entire address space looking for executable code or looking for executable data or finding data. And the Azure Sphere MCUs actually have registers that allow you to, rather than return a zero, return an undefined instruction that forces an undefined instruction exception. So this is just to give you a sense of the defense in depth we're bringing to the table here in MCU to make sure that as hackers do find ways to start chaining attacks, they have to overcome many more obstacles than they typically would to gain access to the device's most trusted portions of its software. So Cortex-M, when you have a Cortex-A and you're running Linux, the best you can do is typically soft real time. We're not even promising that. It's great for connectivity, but if you really need deterministic execution or real-time execution, you really need something like a traditional MCU. Well, what we've been able to do is provide that without linking it to connectivity, without also exposing that core to the internet, because we have these core mappers that are protecting the Cortex-M from the rest of the system. So we can skip a couple of these. So where are we with these Azure Sphere MCUs? Well, MediaTek has publicly announced their chip. It's available now. You guys can go on Amazon if you want and go purchase an Azure Sphere dev kit and start playing with it. And 12 other silicon partners have announced their intents to build Azure Sphere MCUs. And the reason they're doing that is we've effectively told them we will give away the Azure Sphere, the design and silicon design for the Pluton subsystem and all of the IP and patents for these core mappings, obsolescence defense, as well as resource isolation in silicon, as long as they make one that we can run our software on. And so that's the partnership we're offering. They can also sell them on their own products, but we so firmly believe in the silicon security we're offering in this space. We want to make sure everybody can use it, so we're licensing it for free. So I want to pivot a little bit to the OS. This is not a super deep dive into the OS, but I think it provides enough to give you a sense of what's happening. If you look at the operating system stack, at the bottom is a security monitor. So we use kind of in Trust Zone. In Trust Zone parlance, the security monitor is Secure World, and that runs Secure World. It has very limited functionality. It basically interacts with the core mapper. It maps peripherals safely. It's the only entity that's allowed to write to Flash, as an example, and it's basically used for resource and hardware arbitration. This idea of Secure World and Trust Zone, it goes throughout the chips. The core mappers are actually Trust Zone aware. So this is how it can actually tell that if something's executing in Secure World, then you're allowed to, let's say, interact with the core mapper. If it's not executing in Secure World, even if someone, and by the way, Linux does not execute in Secure World because we don't fully trust it, then a lot of these trusted pieces of functionality in silicon just ignore the request. The next level is the Linux kernel that runs in normal world, and it's responsible effectively for connectivity. It's where our TLS stack runs, as an example. Then we have these we're called on-chip cloud services. It's where we run our interactions, our daemons, effectively. Daemons that interact with update, that interact with failure reporting, and basically our first-party applications, how you can think of them. The applications that are published in Microsoft that help run the operating system. And at the top, we have containers. Now, when I use the word containers, please don't think Docker. I think Docker requires 124 megs of RAM. It says 4 megs of RAM. It doesn't fit. These are really sandboxes. So you have sandboxes on the A7 for limiting what the application can do. And on the M4, this stack doesn't exist. I know this says Cortex-Ms. The Cortex-Ms are running in bare metal in this isolated execution environment. So a little more detail that you might appreciate. The security monitor, as I mentioned, protects these critical resources and maps them to different cores. It also implements a boot check. So typically in an MCU space, you're dealing with NOR flash. NOR flash, like go back to the 90s, this is execute in place. So our Linux kernel doesn't execute out of RAM, it actually executes out of flash. So the NOR flash is readable, just like regular memory. It's not writable, it ignores writes, so it's an extra layer of protection. And the security monitor actually implements erasure coding across flash. These are devices that has to run for a decade without being looked at or interacted with, and so that means we have to guard against things like flash corruption. The Linux kernel, the way we implement our access control policy in the Linux kernel is through a Linux security module that examines requests coming in and then makes requests through the security monitor in terms of access, guaranteeing access to resources. We have a capability system behind that to make sure that you have a capability before you're allowed to ask granted permission to access something. And then these on-chip services, for example, is where mutual authentication and TLS take place. So let's move to the cloud and look at what we talk about, what the benefit is when we talk about mutual attestation. So the Azure Sphere Security Service has 3 pieces of functionality. When I talk about brokering trust, what does that mean? It allows us to effectively export a token, a security token, that says that Microsoft has vouched for the security of the device recently. And I'll get in a moment to what that means. It also runs update, so you're able to globally update devices around the world and take failure reports so that you can start to see if you have a lot of devices failing in a certain way to gain some insight into it and see why. So what does this mean? When a device first connects to Azure, it authenticates Azure because we have a PIN, public certificate, but Azure has no idea whether this is actually an Azure Sphere device and whether it's healthy. So I mentioned earlier remote attestation. For those of you not familiar with it, remote attestation allows us to do is to send a challenge down, and then in addition to secure boot, we're using measured boots. We're measuring basically what we're booting with. And then the Azure Sphere chip in silicon takes the measured boot value and signs it along with the nonce and sends it back up to our security service. Security service is going to look at this signature and determine that the device is authentic because only the device has access to that private attestation key. And then it can look at the hash value and effectively determine whether or not it's running software that's genuine, that effectively the measured value is known. In addition to that, we have the ability to take certain measured values and declare them as untrusted. So if there's a significant attack or a significant weakness that we've patched, in addition to on-die rollback protection, the Azure Sphere Security Service can declare certain software releases untrusted, so it will refuse to complete attestation successfully. So what happens when attestation completes successfully? Well, we issue a certificate back to the device that contains its public device ID, and it's signed by Microsoft. And this device ID can then be presented to any online service. So Azure Sphere doesn't require Microsoft or the Azure Cloud. It can work with Amazon, AWS, it can work with Google Cloud if you wanted to. As long as a service can validate the public certificate chain that the device is sent up, it knows that Microsoft is vouched for the health of the device. So you might wonder, well, what happens then when the device goes bad? How do we revoke that certificate? Well, we've leveraged the fact that you can set quick expirations, and we actually have these device certificates expire every day. So when the device gets a certificate after attestation completes, it actually expires after 24 hours. And that's a tunable parameter. But what you can think about is that that 24-hour boundary is the amount of time a device can start to misbehave without being forced to go through attestation again. This means we don't have to manage a certificate revocation list, a CRIL, and for devices, for billions of devices around the world, we simply allow the certificate's own expiration policy to ensure that we go through attestation on some regular cadence. If attestation doesn't complete successfully, we can actually effectively quarantine the device. So the device actually gets two different certificates, one that allows it to connect to Microsoft's update service, and another one that it's allowed to export to other services. And that second certificate simply isn't issued, which means the only service the device is allowed to connect to with TLS is update, which means we can effectively force it to go through a software update and prevent it from connecting to other services. So this method of taking advantage of the certificate infrastructure that we have to effectively use certs as a token and allow Microsoft to vouch for its health is, I think, somewhat interesting use of the attestation of the infrastructure. I know this has been talked about as well in terms of Intel's SGX and some other infrastructure. We're leveraging it here as well. It's just a slide. I don't know how many of you have actually written code for MCUs. It's often really painful. You don't have Eclipse usually. You don't have Visual Studio. It's 1985. Sometimes the debugging experience is painful. Sometimes the debugging experience requires tens of thousands of dollars in license fees because it's so hard to debug. So we just said, well, we should leverage existing development tools. There's Visual Studio, and in the future, Visual Studio Code. You can also just use you can just use command line compilation options. So this is just about making it easier to write code for the MCU space because it's too hard right now and too painful. And you don't get to take advantage of all the tools you typically get with a modern development environment. So as I mentioned, Azure Sphere is open, so anybody can build one of these MCUs. We're licensing the Pluton security subsystem for free because we want people to take advantage of these unique security capabilities. Of course, we're Linux and GPL'd, which means you can go grab the Linux kernel if you want to that we're using and go build it yourself. We make sure that the kernel we're building is also buildable by anyone else who wants to download it. And it's open to any cloud. So by taking advantage of this certificate infrastructure, you can stand up your own Apache web server in your basement if you want and make sure that Azure Sphere devices can mutually authenticate to it, and you can be sure you're actually talking to an Azure Sphere device and not something else. The other thing that's somewhat interesting, I feel like I'm always paying for subscriptions. I feel like everything in my life has turned into a subscription. I feel like I can't buy anything more and be done with it. It doesn't seem to exist anymore. Azure Sphere doesn't have a subscription. When you look at devices, these low-cost devices, people are really sensitive about cost. If you ask someone in one of these MCU spaces, the first thing they're going to ask you is, well, how much is it going to cost for the lifetime of the device to secure it? And what if I don't care about the device in 10 years, but I still care about security? How much will that cost me? Do I have to pay every month? So Azure Sphere is a one-time fee. The one-time fee, it's effectively a little license that comes with the chip. And then that says that you get OS updates and application updates for 13 years. You use the security service for 13 years. And you get a license to the OS for 13 years, which is extendable. If you want to dip your toes in the water, if you're going to AWS, you're going to Azure IoT as an example, to get telemetry, then you're paying a subscription. But if you turn all of that off, we're going to guarantee that we're going to continue to update the device and, with the latest patches and keep it secured for a long period of time. This might seem obvious to this audience, but in the MCU space right now, some of the state-of-the-art in IoT says we have to pay a per device per month fee, which means that every month someone who cares about their costs has to step back and ask, do I care about security this month? Or am I turning off security this month per device? And we really felt strongly that the base security services should be a one-time fee so you don't have to worry about it again. So that's something that we've incorporated into the device. So that's the summary of Azure Sphere. I wanted to look ahead a little bit with the few minutes I have remaining before we can take questions and chat. When I think about where we're headed and what we're trying to do, I first just want to start with something concrete in terms of where we're looking ahead in terms of research. If you looked at that diagram and you asked yourself, what's the riskiest part of that software architecture? The riskiest part of that software architecture is the application code. Because the application code is going to be written by someone who may think it's great that you're providing 13 years of updates. They're going to write the app once, fire it off, and forget it. Even worse, I was at a meeting in Washington with some of the government agencies there, and they said they have what they call fly-by-night operators, where they find an IoT device, they find a significant vulnerability that's being attacked, and then they go find the manufacturer, and the manufacturer's out of business. It was in business 6 months ago, it's out of business. And then they say, oh my gosh, how do we patch a device where no one knows where the code is, and the manufacturer's gone out of business, sometimes purposefully, because they've sold all the devices they can and they want to start a new business. It's a huge problem. Application code is a huge problem. I know we were just talking about Rust. Is that an option? Right now we expose C. It's the only language. This is an early product. It's the first language we're exposing, mainly because MCU developers are used to C. But we have a project with David Tarditi. Some of you might know him from the compiler community and programming languages community. And he's developed something called Check-C. You can go check it out on GitHub using Clang. It's an attempt, basically backwards compatible version of C that protects against a lot of the most egregious security problems in the language. And so as he's maturing that work, and he's published a few papers on it, our goal is to take that into the product and offer Check-C as part of a core product offering. We're also looking at other languages and how to support them. And we talked about, .NET Core and Java are a bit too big. A typical application right now has 200K of RAM that it gets to use. You can't really build in a full language runtime. So there's this interesting space that we're in of trying to bring a lot of these more fully featured features or languages down into the device itself. Now you might ask, what's Azure Sphere written in? We're talking about C and its riskiness. The Linux kernel, of course, is written in C. Everything else in our operating system, including portions of our bootloader, are all written in modern C++. So we actually use something called, I don't know if you know about this, Electronic Arts has an embedded STL library called EASTL. We leverage that so that we get a lot of the benefits of, at least some benefits in terms of type safety and making it easier to test code, making it easier to build abstractions around code using C++. So that's a little bit in terms of what we're doing now in terms of Check-C. Alec and I talked to me and said, well, what else would you talk to about this audience? Well, I can talk to you about my fears. I think we're entering this unprecedented era where you have the confluence of three things: mobility, incredibly cheap mobility, incredibly cheap connectivity, and incredibly inexpensive cameras and MCUs. So what do I mean by that? Well, this is what I'm seeing right now all over the place in the news, is machine learning combined with really cheap mobility, really cheap cameras, really cheap MCUs means that our face, which Apple tells me is unique, being taken everywhere without any knowledge or any control on my part. And a lot of times I see drones all over Bellevue all the time with cameras. I wave at them. I don't have much more control than that. This is on the left-hand side was an article, I believe in the Wall Street Journal, about outfitting police officers in China with facial recognition glasses so that they can constantly be tracking and scanning and tracking your movements. There's a recent article that discovered that several airplane manufacturers, which is I consider somewhat mobility, actually have cameras in the backs of their in-flight recording systems, so they can snap pictures of what you're watching and see how your face reacts and basically train their ML algorithms. Although some of them have said, wait, we promise those cameras are off. I don't know how you guarantee that. And then the palm of your hand. That is the smallest drone with a camera that can take pictures I found yet. So that's able to fly around and take pictures of you. So what I wonder is, I worry about two things. I don't know if we can stop the tsunami of drones, cameras, and mobility. I think that's the era we're entering. But we can think about privacy. And there's two problems I think about. One, when I was talking about this at Berkeley, and the question was, can you create a convincing case where machine learning and facial recognition should be done locally on device and not remotely? So why would you ever do that? Bandwidth is cheap, the cloud is cheap. Well, privacy. Is it possible to construct a facial recognition system, especially when thinking about mobility, where you can guarantee that people who aren't being searched for, I think about security a lot, I think about facial recognition at airports as an example that's happening now, that your face isn't constantly, that you only track faces that are, let's say, people of interest, if that's a thing we can think about, rather than everybody being uploaded and tracked all the time. Is it possible to create a architecture around privacy to protect us in terms of this onslaught of facial recognition that I see everywhere? The other one is that can you prove a model that doesn't allow invisible people? What do I mean by invisible people? I think about facial recognition at airports. I think about the fact that I'm probably being recognized and tagged all the time. I've never heard of any provable model to prove that a facial recognition model doesn't have gaps, that Alec wouldn't be invisible. So when he would walk through, no facial recognition model would ever see him, but they would always see me, right? Because he is special. How do we? I feel like machine learning and deep neural nets have run ahead in terms of these incredible capabilities, and we're scrambling to catch up and think about how we think about privacy and security in this space. What's the power of RSA? The power of RSA was a public, transparent, and provably correct model for cryptography, that anyone could at least know that if they were using an RSA or using a library that implemented RSA that maybe even verified, they're getting some base foundations in terms of security, in terms of privacy of their communication. Same with ECC, at least as far as we know. I don't think everyone agrees those haven't been hacked, although over coffee, let's talk about TPMs and problems with proving primality. Where are provable guarantees in machine learning? I think that we've only just begun seeing this huge wave of basically people and devices that are mobile, that are filming and tracking everything. And if you told me 10 years ago we're going to release 10 million or 100 million or 500 million cameras, I would say that's fine. There's too much data, and you won't be able to do anything with it. But once you add deep neural nets and facial recognition, suddenly it becomes scalable and tractable. And I think there's a real opportunity for us as a community to step back and say, well, how do we provide some sort of guarantees in terms of security and privacy in this space? So that's what I think about. I really want to thank you for the opportunity to be here and to talk about Azure Sphere. I'll be here all day and into the banquet tonight. I'm happy to talk more about this and take your questions. So thank you very much.